Just 4.2 light-years away, orbiting the closest star to our Sun, lies a world that could change everything we know about our place in the universe. Proxima Centauri b, a planet roughly the size of Earth, sitting in the habitable zone where liquid water might exist. It's right there, our nearest potentially life-bearing neighbor, tantalizing us with possibilities. But here's the crushing truth. We will never reach it. Not in our lifetimes, not in our children's lifetimes, and probably not for thousands of years, if ever. Today, we're diving into the brutal physics, the staggering distances, and the fundamental barriers that make this cosmic neighbor forever out of reach. If you're fascinated by the limits of human exploration and the mysteries of our cosmic neighborhood, make sure to subscribe to this channel and give a thumbs up. And one quick question. If you could send one message to Proxima Centauri b that would arrive in 4.2 years, what would you say? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let me start by painting you a picture of just how far away Proxima b actually is. When we say 4.2 light-years, those words roll off the tongue easily, almost casually. But the reality is mind-shattering. Light traveling at 299,792 kilometers per second, the fastest thing in the universe, takes 4 years and 2 months to cover that distance. That's 40 trillion kilometers. 40 trillion. To put this in perspective, if you could drive to Proxima b at highway speed, it would take you 48 million years. The Voyager 1 spacecraft, humanity's most distant emissary, launched in 1977 and is currently our fastest object ever sent into interstellar space. After 46 years of travel, it's moving at about 17 kilometers per second, roughly 60,000 kilometers per hour. That sounds fast until you realize that at this speed, Voyager 1 would need 73,000 years to reach Proxima Centauri. 73,000 years ago, modern humans were just beginning to leave Africa. The pyramids wouldn't be built for another 70,000 years. That's how long this journey would take with our current fastest technology. But it gets worse. Voyager wasn't designed for interstellar travel. It just happened to gain enough speed from its planetary flybys to escape the solar system. The Parker Solar Probe, our fastest spacecraft designed for speed, reaches velocities of 640,000 kilometers per hour when diving close to the Sun. Even at this blistering pace, a journey to Proxima b would still take over 6,000 years. 6,000 years ago, humans were just inventing the wheel. The fundamental problem is energy. To accelerate any significant mass to speeds that would make interstellar travel feasible, say 10% the speed of light, requires energy that makes our most powerful rockets look like firecrackers. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, reveals the cruel mathematics of space travel. The amount of fuel needed increases exponentially with your desired speed. To reach even 1% of light speed using conventional chemical rockets, you'd need a fuel-to-payload ratio so extreme that your spacecraft would essentially be a tiny capsule attached to a fuel tank the size of a planet. Let's talk about the Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. This ambitious project proposes sending tiny spacecraft, each weighing just a few grams, to Proxima Centauri using powerful lasers to push them via light sails. The plan is to accelerate these starships to 20% the speed of light, which would cut the journey time to about 20 years. Finally, something that sounds achievable in a human lifetime, right? But here's where reality intrudes. To accelerate these gram-scale probes to 20% light speed, you'd need a laser array generating about 100 gigawatts of power, equivalent to the output of 100 nuclear power plants, all focused on a sail just a few meters across. The technological challenges are staggering. The sail must be incredibly reflective, incredibly thin, and able to withstand temperatures that would vaporize most materials. The laser must maintain focus over millions of kilometers as the probe accelerates. And this is for a spacecraft so small it couldn't carry anything larger than a microchip. Even if we solved all these technical challenges, the Starship would face another brutal reality. It can't slow down. At 20% light speed, it would zip through the Proxima Centauri system in a matter of hours, barely having time to take a few snapshots before disappearing into interstellar space forever. There's no braking system, no way to decelerate without doubling the mass and complexity of the mission. It's a cosmic drive-by, not a visit. And we haven't even discussed the hazards of interstellar space. Between here and Proxima Centauri lies what we call the local interstellar medium. And it's not empty. There are stray atoms of hydrogen, dust grains, and cosmic debris. At normal spacecraft speeds, these pose minimal danger, but at 20% the speed of light, a collision with a dust grain the size of a small pebble would release energy equivalent to several kilograms of TNT. Even individual hydrogen atoms become deadly projectiles, slamming into the spacecraft with enormous energy. A ship moving at this velocity would need shielding so thick it would defeat the entire purpose of making the probe lightweight. The Voyager probes have given us our first taste of interstellar space. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. The environment out there is stranger than we imagined. Cosmic rays, high-energy particles from exploding stars, bombard everything constantly. The interstellar magnetic field twists in unexpected ways. The density of particles fluctuates unpredictably, and this is data from our immediate cosmic neighborhood. We have no idea what conditions are like across the vast gulf between us and Proxima Centauri. Let's talk about radiation, one of the most insidious barriers to reaching Proxima b. Space is flooded with cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events. On Earth, we're protected by our atmosphere and magnetic field. The International Space Station, orbiting just 400 kilometers above Earth's surface, still receives some protection from our planet's magnetosphere. But astronauts there receive about 150 millisieverts of radiation per year, roughly 50 times more than the average person on Earth. On a journey to Proxima b, there would be no protection at all. The spacecraft would be bombarded by galactic cosmic rays for decades or centuries. These particles don't just cause cancer, they rip through DNA, damage the central nervous system, and can cause immediate radiation sickness at high enough doses. To protect a human crew, you'd need shielding so thick and heavy that accelerating it to any significant fraction of light speed becomes impossible. Some scientists have proposed using water or hydrogen as shielding, since these elements are effective at stopping radiation. But we're talking about meters of shielding surrounding the entire habitable area, adding tons upon tons of mass. The twin study conducted by NASA comparing astronaut Scott Kelly, who spent a year in space with his identical twin Mark, who remained on Earth, revealed disturbing changes. Scott's telomeres lengthened in space but then rapidly shortened upon return, his gene expression changed, and his cognitive performance declined. This was after just 1 year in low Earth orbit, still partially protected by Earth's magnetic field. Imagine the biological damage from decades in deep space, with no protection and no way to turn back. Speaking of the incredible distances within our own cosmic neighborhood, and the challenges of leaving even our solar system, I've explored this topic in depth in another video. Check out How Big is the Solar System and Why We Might Never Leave It, where we dive into the mind-boggling scale of our own backyard and why it presents such formidable obstacles to exploration. The link is in the description below and on the card above. Now let's consider a different approach, generation ships. If we can't make the journey in one lifetime, what if we built a massive spacecraft where multiple generations would live, reproduce, and die during the centuries-long voyage to Proxima B? This concept has captivated science fiction writers for decades, but the engineering realities are nightmarish. First, there's the minimum viable population problem. Geneticists estimate you'd need at least 10,000 people to maintain genetic diversity and avoid the problems of inbreeding over many generations. Some studies suggest even this might be too few. Now consider that each person needs food, water, air, living space, and waste recycling for their entire lives. The spacecraft would need to be a fully self-sustaining ecosystem, essentially a miniature Earth. Biosphere. 2. A 3.1-acre structure built in Arizona in the early 1990s attempted to create a closed ecological system. It housed 8 people for 2 years. The experiment was plagued with problems. Oxygen levels dropped dangerously low, carbon dioxide spiked, most vertebrate species died, and the project had to pump in oxygen from outside to prevent the inhabitants from suffocating. And this was on Earth, with access to replacement parts, emergency supplies, and the ability to abort the experiment. A generation ship would have no such safety nets. The psychological challenges of a generation ship are equally daunting. Studies of isolated communities, Antarctic research stations, submarines, Mars analog habitats consistently show that humans struggle with confinement and monotony. People develop depression, anxiety, and interpersonal conflicts even when they know the isolation is temporary. On a generation ship, there would be no end date, no emergency escape, no possibility of seeing Earth again. Children would be born into a metal tube, never experiencing rain, oceans, or forests. Would they maintain their ancestors' drive to reach Proxima B, or would they revolt against a mission they never chose? The technological challenges are equally staggering. Every system on the ship would need to function flawlessly for centuries. There are no replacement parts except what you bring or can manufacture on board. Metals fatigue, seals degrade, electronic components fail. The ship would need complete manufacturing capabilities, essentially a flying factory, to produce everything from computer chips to medical supplies to spare parts for critical life support systems. The complexity is beyond anything humanity has ever attempted. Then there's propulsion. Even a generation ship needs to accelerate and eventually decelerate. Nuclear pulse propulsion, using nuclear explosions to push the ship forward, was seriously studied in the 1950s and 60s under Project Orion. The concept works on paper. Detonate nuclear bombs behind a massive pusher plate, and the explosions accelerate your ship. But you'd need thousands of nuclear weapons, a pusher plate weighing thousands of tons, and shock absorbers that could handle nuclear blast after nuclear blast without failing. The whole design violates the Partial Test Ban Treaty, and the engineering tolerances required have never been demonstrated. Fusion propulsion offers a cleaner alternative. The proposed Project Daedalus, designed by the British Interplanetary Society in the 1970s, envisioned a 2-stage fusion rocket that could reach 12% of light speed. But we still haven't achieved sustained fusion power generation on Earth, let alone built a fusion rocket capable of accelerating thousands of tons to relativistic velocities. The technical gaps between our current capabilities and what Daedalus required are enormous. Some scientists have proposed using antimatter as fuel. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, far more efficient than any chemical or nuclear reaction. The problem? We can currently produce antimatter only in minuscule quantities at particle accelerators like CERN. It takes 10 billion times more energy to create antimatter than you get back when it annihilates. And storing antimatter, which destroys anything it touches, would require magnetic containment systems of unprecedented sophistication. Let's examine what we actually know about Proxima b itself, because here's an uncomfortable truth: we might be chasing a mirage. Discovered in 2016 by the European Southern Observatory using radial velocity measurements, Proxima b reveals itself only through the tiny wobble it induces in its parent star. We've never directly imaged this planet. We don't know if it has an atmosphere, oceans, or even a solid surface. It could be a barren rock, a water world, or something completely unlike anything in our solar system. Proxima Centauri, the star it orbits, is a red dwarf, much smaller and cooler than our Sun. It's also violently active, unleashing powerful stellar flares that could strip away any atmosphere Proxima b might have. In 2017, Proxima Centauri released a flare so intense it increased the star's brightness by 1,000 times for 10 seconds. The radiation from such flares would be devastating to any life on the planet's surface. Unlike Earth, which orbits our relatively calm Sun at a safe distance, Proxima b huddles close to its host star to receive enough warmth, putting it directly in the line of fire. The planet is likely tidally locked, meaning one side perpetually faces the star while the other remains in eternal darkness. This happens to planets orbiting close to their stars, just as our Moon always shows Earth the same face. On Proxima b, one hemisphere would be scorched by constant radiation, while the other freezes in permanent night. Only a narrow twilight zone between these extremes might be habitable if the planet has a thick enough atmosphere to redistribute heat. But that's a big if. Recent observations from the James Webb Space Telescope have revolutionized our ability to study exoplanet atmospheres, but Proxima b presents unique challenges. Its proximity to the bright stellar disk of Proxima Centauri makes atmospheric characterization extremely difficult. We're trying to detect the faint signature of an atmosphere while staring into what amounts to a cosmic spotlight. As of now, we simply don't know if Proxima b has the conditions necessary for life or even habitability. Let's talk about communication, because even if we somehow sent a mission to Proxima b, staying in touch would be agonizing. Radio signals travel at the speed of light, meaning a message from Earth to Proxima b would take 4.2 years to arrive. A reply would take another 4.2 years to come back. That's an 8.4-year round-trip communication delay. You could ask a question and receive an answer nearly a decade later. If something went wrong on the mission, Earth would learn about it more than 4 years after the fact, far too late to offer any assistance. The power requirements for interstellar communication are staggering. The Voyager spacecraft, now over 22 billion kilometers from Earth, transmits with a 23-watt signal, about the same as a refrigerator light bulb. Yet NASA's Deep Space Network, using 70-meter dish antennas, can barely detect Voyager's whisper across that distance. To communicate from Proxima Centauri, you'd need either enormous transmitter power or impossibly large antennas, or both. A small probe like the proposed Starship wouldn't have the power budget or the antenna size to send anything more than the most basic data. Here's another sobering reality: the cosmic coordinate problem. Proxima Centauri isn't stationary relative to the Sun. Both stars are moving through space at different velocities. Proxima Centauri is currently approaching us at about 22 kilometers per second. In the time it would take a slow spacecraft to reach it, say 10,000 years, both stars will have moved significantly. Your spacecraft would need to constantly update its trajectory, making real-time calculations about where Proxima Centauri will be when the ship finally arrives. Any error in these calculations, compounded over millennia, could mean missing your target by light years. The navigation challenges extend beyond just pointing in the right direction. In interstellar space, there are no landmarks, no GPS satellites, No convenient asteroids to use for course corrections. The spacecraft would need to navigate using pulsars, rapidly spinning neutron stars that emit precise radio pulses as cosmic lighthouses. NASA's NICER instrument on the ISS has demonstrated pulsar-based navigation in Earth orbit, but doing this across light years with limited power and degraded instruments would be extraordinarily difficult. Let's consider the biological impossibility of human survival on such a journey. We evolved on Earth, adapted to 1 g of gravity, a 24-hour day, and the full spectrum of our sun's light. In space, everything works against us. Microgravity causes bone loss about 1 to 2% per month. Astronauts on the ISS exercise 2 hours daily just to slow this deterioration. On a decades-long journey, even with exercise, crew members would arrive at Proxima b with skeletal structures too weak to support their own weight, even in the planet's lower gravity. Muscle atrophy accompanies bone loss. The heart, which doesn't need to work as hard in microgravity, shrinks and weakens. When astronauts return to Earth after 6 months in space, they can barely stand. They require extensive rehabilitation to walk normally again. Imagine arriving at Proxima b after decades in space, too weak to explore, with bones like glass and hearts struggling to pump blood against even partial gravity. The immune system weakens in space. T cells don't function properly, making astronauts more susceptible to infections. Wounds heal more slowly. Dormant viruses like herpes simplex can reactivate. On Earth, we're surrounded by a biosphere that trained our immune systems through constant low-level exposure. In the sterile environment of a spacecraft, immune systems atrophy. A minor infection that would be trivial on Earth could become life-threatening on an interstellar voyage. Vision problems plague long-duration space travelers. Fluid shifts in microgravity increase pressure on the optic nerve, causing it to swell and the eyeball to flatten. Many astronauts return from space with permanently degraded vision. The condition, called spaceflight-associated neuroocular syndrome, affects about 70% of astronauts on long missions. There's currently no way to prevent it except by providing artificial gravity, which requires a rotating spacecraft with all its own engineering nightmares. The psychological toll of interstellar travel might be the most insurmountable barrier of all. Humans are social creatures who evolved in tribes connected to nature, with varied experiences and the freedom to roam. On an interstellar mission, you'd be trapped in a metal container with the same people for decades. No new faces, no privacy, no escape. The Antarctic winter over syndrome shows us what happens to isolated groups. Increased irritability, depression, cognitive decline, and sometimes complete psychological breakdown. And that's with the knowledge that spring will come, that rescue is possible, that Earth is still beneath their feet. Consider the phenomenon of Earth out of view syndrome that some psychologists predict for deep space travelers. Throughout human history, we've always been able to see our home, whether it's our village, our country, or our planet. Mars astronauts will still see Earth as a bright star, but travelers to Proxima b would watch Earth fade until it's indistinguishable from any other star. That psychological tether to home, severed forever, could trigger existential crises we can't predict or prepare for. The confined environment would breed its own pathologies. Personal space would be a luxury, privacy almost non-existent. Every argument, every personality clash, every minor annoyance would be magnified by the inability to escape. Studies of submarine crews show increased aggression and decreased cognitive performance after just 90 days. Multiply that by 1,000 for an interstellar journey. The risk of violence, mutiny, or psychological collapse would be constant. Sleep disorders would plague the crew. Without Earth's natural day-night cycle, circadian rhythms drift. The ISS uses artificial lighting to simulate Earth days, but it's imperfect. Astronauts commonly suffer from insomnia, fatigue, and the cognitive impairment that follows. Over decades, chronic sleep deprivation would compound, affecting decision-making, emotional regulation, and physical health. Mistakes that could doom the mission become more likely with each passing year. Let's talk about something even more fundamental. Time itself becomes your enemy on interstellar journeys. Not just the decades or centuries of travel time, but the effects of time dilation as described by Einstein's special relativity. If we could somehow accelerate a spacecraft to a significant fraction of light speed, say 90%, time would pass more slowly for the travelers than for those left behind on Earth. A journey that takes 10 years for the crew might see 20 years pass on Earth. This creates profound philosophical and practical problems. If you left Earth with a specific mission, establish a colony, conduct research, make contact, by the time you arrive, Earth's priorities might have completely changed. The government that sent you might no longer exist. The technology you're carrying could be obsolete. Worse, a faster ship launched decades after you could arrive first, making your entire journey pointless. Imagine spending your entire life traveling to Proxima B, only to find a thriving colony established by people who left Earth long after you did. The resource management challenges of interstellar travel are staggering. Every atom of matter on your spacecraft is precious because you can't get more. Water can be recycled, but not with perfect efficiency. The ISS recovers about 93% of water from urine and humidity, but that 7% loss adds up over time. Over a century-long journey, you'd need to start with far more water than the crew would ever use at once, just to account for recycling losses. Food presents an even bigger challenge. You can't pack centuries' worth of meals. The spacecraft would need a complete agricultural system, essentially a farm in space. But growing food requires water, nutrients, and energy. Plants need specific wavelengths of light, which means power-hungry LED arrays. They produce oxygen, which sounds great until you realize that oxygen levels need precise regulation. Too much is as dangerous as too little. The entire ecosystem would need constant monitoring and adjustment. Mechanical systems would face unprecedented challenges. On Earth, we design machines to last decades at most. Cars might run for 20 years with maintenance. Buildings might stand for a century, but interstellar spacecraft would need systems that function for far longer. Seals degrade, metals fatigue, electronics fail. The Voyager probes, our longest operating spacecraft, have lasted 46 years by shutting down non-essential systems and operating on minimal power. An interstellar mission couldn't afford such compromises. Life support can't be turned off to save power. Consider something as simple as air. The ISS requires regular resupply of nitrogen to maintain atmospheric pressure. Tiny leaks are inevitable. No seal is perfect. Over centuries, these microscopic losses would add up. The spacecraft would need not just air recycling, but the ability to manufacture new gases from raw materials. That means mining equipment, chemical processing facilities, and storage for volatile gases, all adding mass and complexity. The manufacturing capabilities required boggle the mind. You'd need to produce everything from antibiotics to microchips. 3D printing helps, but you still need raw materials and incredibly precise equipment. A single critical component failing, say, the computer controlling life support, could doom the mission if you can't manufacture a replacement. The spacecraft would need multiple redundant manufacturing systems, each capable of producing the others in case of failure. Power generation over centuries presents unique challenges. Solar panels degrade and become less efficient over time. Nuclear reactors require fuel and produce waste that must be safely stored. Fusion reactors, if we could build them, would need a supply of fuel, likely deuterium and tritium, that would last the entire journey. Any power system would need maintenance, replacement parts, and backups for the backups. A power failure in interstellar space means death with no possibility of rescue. Let me share something that really drives home the impossibility of this journey. The Breakthrough Starshot project, our most realistic proposal for reaching Proxima b, aims to send gram-scale probes. But even this modest goal faces seemingly insurmountable challenges. The laser array needed would cost hundreds of billions of dollars. It would need to be built in space or at high altitude to avoid atmospheric interference. The pointing accuracy required, keeping a laser focused on a meter-wide sail across millions of kilometers, exceeds anything we've ever achieved. The sail material itself pushes the boundaries of materials science. It needs to be incredibly thin, just atoms thick, yet strong enough to not tear under acceleration. It must reflect nearly 100% of the laser light, or it will overheat and vaporize. We're talking about materials that don't yet exist, manufactured with precision we can't yet achieve, deployed in ways we haven't figured out. Even if Breakthrough Starshot succeeds, what do we get? A few images transmitted back over 4 years from a probe moving so fast it crosses the Proxima system in hours. No samples, no detailed study, no possibility of follow-up. It's like trying to understand New York City from a single photograph taken from a speeding car. The scientific value, while not zero, hardly justifies the enormous cost and effort. The communication challenge for even these tiny probes is daunting. At 20% light speed, the probe's signal would be significantly redshifted, changing its frequency and making it harder to detect. The transmitter would need to be powerful enough to send a signal across 4 light-years, yet small enough to fit on a gram-scale probe. The receiving equipment on Earth would need to be orders of magnitude more sensitive than anything we have today. Here's a reality check about our current space capabilities. The farthest humans have ever traveled is to the Moon, about 384,000 kilometers. Proxima b is 100 million times farther. We've sent exactly 12 people to walk on another world, and none since 1972. The ISS, humanity's permanent outpost in space, orbits just 400 kilometers up and requires constant resupply from Earth. We haven't even sent humans to Mars yet, our nearest planetary neighbor. The James Webb Space Telescope, one of our most advanced space instruments, took 30 years to develop and cost $10 billion. It operates at the L2 Lagrange point, just 1.5 million kilometers from Earth, a mere fraction of the distance to Proxima b. If building and deploying a telescope that close to Earth required 3 decades and the resources of multiple nations, imagine the time and cost of an interstellar mission. Our robotic explorers fare better but still face limits. New Horizons, which gave us our first close-up images of Pluto, travels at about 16 kilometers per second. At that speed, it would take 78,000 years to reach Proxima b. The spacecraft is already running low on power, its plutonium power source decaying with a half-life of 88 years. By the time it's traveled even 1% of the distance to Proxima b, it will be a dead, frozen relic drifting through space. Let's address the elephant in the room. Faster than light travel. Science fiction has given us warp drives, hyperspace and wormholes, but physics remains stubbornly uncooperative. Einstein's special relativity sets the speed of light as an absolute cosmic speed limit. It's not just a rule, it's woven into the fabric of space-time itself. As you approach light speed, your mass effectively becomes infinite, requiring infinite energy to accelerate further. This isn't a technological limitation we might overcome, it's a fundamental property of the universe. Some physicists have proposed exotic solutions like the Alcubierre drive, which would warp space-time to move space around a ship, rather than moving the ship through space. But this requires exotic matter. With negative energy density, something that may not exist, and certainly can't be manufactured with any known technology. Even if exotic matter exists, the energy requirements are absurd, equivalent to converting the mass of Jupiter entirely into energy. Wormholes, another science fiction favorite, are theoretically possible solutions to Einstein's equations. But naturally, occurring wormholes, if they exist, would be microscopic and unstable, collapsing faster than light could traverse them. Creating an artificial wormhole would require manipulating space-time on a scale that makes even Kardashev Type 3 civilizations look primitive. We're talking about engineering on the scale of solar systems, not spacecraft. The economic reality of interstellar travel is equally prohibitive. The Apollo program, which sent humans to the moon, cost about $280 billion in today's money. That bought us 9 crewed missions to lunar orbit and 6 moon landings. An interstellar mission would cost orders of magnitude more. We're potentially talking about a significant fraction of global GDP sustained over decades or centuries. No government or corporation could justify such an expense, especially with no possibility of economic return. Consider the opportunity cost. The resources required for an interstellar mission could instead fund thousands of robotic missions within our solar system, cure diseases, address climate change, or lift billions out of poverty. From a purely utilitarian perspective, interstellar travel makes no sense when we have so many pressing needs at home and so much left to explore in our own cosmic backyard. But perhaps the most breaking reality is this. Even if we somehow overcame every technical, biological, and economic barrier, even if we built generation ships or developed revolutionary propulsion, even if we kept crews alive and sane for the journey, we still might arrive to find nothing. Proxima b might be a barren rock, its atmosphere stripped away by stellar flares. It might be locked in a permanent ice age or shrouded in a toxic atmosphere. We could spend centuries traveling to a world no more habitable than Mars or Venus. The search for exoplanets has revealed the cosmos teeming with worlds, but also shown us how rare Earth-like conditions might be. We've found hot Jupiters, mini-Neptunes, super-Earths, and exotic planets unlike anything in our solar system. But we haven't found Earth 2.0. The more we learn about planetary formation and evolution, the more we appreciate the delicate balance of factors that make Earth habitable. Proxima b, for all our hopes, might be just another inhospitable world in an uncaring universe. This brings us to a profound question. If interstellar travel is impossible, are we alone? The Fermi paradox asks why, in a universe billions of years old with hundreds of billions of galaxies, we see no evidence of other civilizations. One possible answer is that interstellar travel is not just difficult, but effectively impossible for any civilization, no matter how advanced. The universe might be full of intelligent life, but each civilization is trapped in its own stellar system, isolated by the vast gulfs of interstellar space. This cosmic quarantine might be a fundamental feature of the universe. Perhaps nature, in its wisdom, keeps civilizations separated to prevent conflicts, preserve diversity, or for reasons we can't fathom. The impossibility of interstellar travel might not be a bug, but a feature, a cosmic speed limit that ensures each world develops independently, each intelligent species following its own unique path without interference. But here's what fills me with wonder, despite these limitations. We know Proxima b exists. We detected a world orbiting another star using nothing but careful observations and mathematical analysis. We can study its orbit, estimate its mass, and speculate about its conditions. Our telescopes grow more powerful each year. The James Webb Space Telescope is already revolutionizing our understanding of exoplanet atmospheres. Future telescopes might directly image Proxima b, analyze its atmosphere, even detect signs of life. We might never walk on Proxima b, but we can still explore it with our minds and instruments. We can build better telescopes, develop new techniques for detecting biosignatures, and gradually piece together a picture of this alien world. In a sense, we're already exploring Proxima b, not with our bodies, but with our intellect and imagination. The photons that left Proxima b 4.2 years ago carry information about that world. When they reach our telescopes, we decode their secrets. This is humanity's superpower. We explore with our minds what we cannot reach with our bodies. We've mapped galaxies billions of light years away, detected gravitational waves from colliding black holes, and photographed the event horizons of supermassive black holes. We've never left Earth's vicinity, yet we've explored the universe from the quantum scale to the cosmic web. Proxima b might be forever out of physical reach, but it's not beyond our intellectual grasp. The story of Proxima b is ultimately a story about limits, but also about transcending those limits through science and imagination. We might be confined to our solar system, but our minds roam free among the stars. Every spectrum we analyze, every exoplanet we discover, every theoretical breakthrough brings us closer to understanding our cosmic neighborhood. We might never shake hands with inhabitants of Proxima b, but we can still unravel its mysteries from afar. So where does this leave us? We will never reach Proxima b, that much seems certain given our current understanding of physics and the vast scales involved, but perhaps the question isn't whether we can get there, but what we can learn from here. Each new telescope, each new observation technique, each new discovery adds another piece to the cosmic puzzle. We're not conquistadors planting flags on distant worlds. We're scholars reading the book of the universe one page at a time. The real tragedy isn't that we can't reach Proxima b, it's that we might stop trying to understand it. The moment we accept our limitations as final, we stop pushing boundaries. Yes, interstellar travel seems impossible now, but so did flight before the Wright brothers, so did leaving Earth's atmosphere before Sputnik, so did detecting exoplanets before Maya and Queloz. The history of science is littered with impossibilities that became merely difficult, then routine. Perhaps our descendants will look back at this video and laugh at our primitive understanding, our limited imagination. Perhaps they'll have found ways around the light-speed barrier that we can't even conceive. Or perhaps they'll have accepted our cosmic isolation, but found richness in exploring our own solar system and understanding distant worlds through ever more powerful instruments. Either way, they'll build on the foundation we lay today. The universe has set the rules. The speed of light is absolute, the distances are vast, and our biology is fragile. But within those rules, human ingenuity has always found ways to expand our reach. We might never touch Proxima b, but every photon we collect from that distant world is a small victory against the cosmic dark. Every spectrum we analyze is a message from across the void. Every discovery reminds us that even if we're trapped in our stellar neighborhood, our curiosity and wonder are boundless. This is why I create these videos, to share both the harsh realities and the incredible possibilities of our universe. If this exploration of cosmic limits and human ambition resonated with you, please subscribe to the channel. Your support helps us continue asking the big questions and confronting the uncomfortable truths about our place in the cosmos. Share this video with someone who dreams of the stars but needs to understand the challenges we face. What do you think? Will humanity find a way to overcome these seemingly insurmountable barriers, or are we destined to remain forever in our cosmic cradle? Share your thoughts in the comments below. And remember, even if we can't reach the stars, we can still reach for them. Until next time, keep looking up, keep asking questions, and never stop wondering about our incredible, frustrating, beautiful universe. Let me take you deeper into the physics that makes interstellar travel such a nightmare. The tyranny of the rocket equation isn't just about fuel, it's about the fundamental relationship between mass, energy, and velocity. Every kilogram you want to accelerate to 10% of light speed requires energy equivalent to burning about 400 million kilograms of coal. That's for 1 kilogram. A human being weighing 70 kilograms? That's 28 billion kilograms of coal-equivalent energy. A small spacecraft weighing 1,000 tons? The numbers become meaningless. We're talking about energy equivalents that dwarf humanity's entire annual energy production. But it gets worse when you factor in the need to decelerate. See, most discussions about interstellar travel focus on acceleration, getting up to speed. But unless you want to zip past Proxima B in a cosmic flyby, you need to slow down. That means carrying fuel, not just for acceleration, but for deceleration too. The rocket equation becomes doubly cruel. You need fuel to slow down the fuel you're carrying to slow down. It's an exponential nightmare that makes the challenge not just difficult, but fundamentally impractical with any reaction-based propulsion system. Consider Project Longshot, a 1980s design study by the US Naval Academy and NASA. They proposed a 400-ton unmanned probe that would take 100 years to reach Alpha Centauri. The design called for a fusion pulse engine powered by helium-3 and deuterium. Sounds reasonable until you realize we have no practical fusion rockets. Helium-3 is incredibly rare on Earth, and the entire design assumed technological breakthroughs that still haven't happened 40 years later. Even this practical design required technology. We don't have to reach a star. We're not even targeting anymore since Proxima B's discovery. The materials science challenges alone are staggering. Every material degrades over time through various processes. Cosmic rays cause atomic displacement, knocking atoms out of their crystal lattice positions. This gradually weakens metals, makes them brittle, and can cause catastrophic failure without warning. On Earth, we can inspect, maintain, and replace degraded materials. On a centuries-long interstellar voyage, you'd need to somehow detect and repair atomic-level damage throughout the entire spacecraft structure while in flight. Outgassing presents another insidious problem. In the vacuum of space, materials slowly release trapped gases. Plastics emit volatiles, metals release absorbed hydrogen, composites break down. Over decades, these emissions can contaminate sensitive equipment, fog optical surfaces, and even create toxic atmospheres in enclosed spaces. The ISS deals with this through careful material selection and constant air filtration, but they also have regular resupply missions. An interstellar spacecraft would need materials that remain stable for centuries in hard vacuum while exposed to temperature extremes and radiation. Temperature management in interstellar space is counterintuitive. While space is cold, about 2.7 Kelvin, getting rid of heat is actually a major problem. There's no air for convection, no nearby matter for conduction. The only way to lose heat is through radiation, which is slow and inefficient. Every watt of power used on board eventually becomes waste heat that must be radiated away. Too much heat and electronics fail, crew quarters become uninhabitable, and materials degrade. Too little heat and fluids freeze, batteries fail, and the crew freezes to death. The ISS uses huge radiator panels to dissipate heat, but these are vulnerable to micrometeorite impacts and degradation over time. An interstellar spacecraft would need radiators that could function for centuries without maintenance or replacement. They'd need to be oversized to account for efficiency losses over time, adding mass. And they'd need to be protected from impacts while still being exposed enough to radiate heat, a design contradiction with no easy solution. Let's talk about what happens to electronics over deep time. Computer chips suffer from electromigration, the gradual movement of atoms in conductors caused by electrical current. Over years, this creates voids and hillocks in the circuitry, eventually causing failure. Cosmic rays cause single-event upsets, flipping bits in memory and potentially corrupting critical software. They also cause latch-up events that can permanently damage circuits. The smaller and more efficient our electronics become, the more vulnerable they are to these effects. The Voyager spacecraft are only examples of long-duration electronics in space, use 1970s technology, simple, robust, and radiation-hardened. But even these are failing. Voyager 2's primary radio system failed in 2020. Various instruments have been shut down to conserve power. The spacecraft are expected to go completely silent by 2030. These probes were designed for a 4-year mission and have lasted over 4 decades, an engineering triumph. But an interstellar mission would need electronics to last 10 times longer minimum, while performing far more complex tasks. Software degradation is real too, not the code itself, but our understanding of it. The Voyager team struggles to make changes because the original programmers are retired or deceased. Documentation gets lost, institutional knowledge fades. Imagine trying to maintain and update software after centuries, with the original developers long dead, the programming languages obsolete, and the hardware architecture ancient by contemporary standards. You'd need not just redundant systems, but complete documentation, training programs, and the ability to rewrite everything from scratch if necessary. Now consider the biological contamination risk. Earth microbes are incredibly resilient. Bacteria have survived on the outside of the ISS, exposed to vacuum, radiation, and temperature extremes. Some organisms can remain dormant for millions of years, waiting for favorable conditions to revive. Any interstellar mission would inevitably carry microbial hitchhikers, despite our best sterilization efforts. These could mutate over the centuries of radiation exposure, potentially becoming dangerous to the crew or contaminating any world we reach. The reverse is equally concerning. If Proxima b harbors life, even microbial life, it could be utterly alien to Earth biology. Our immune systems evolved to handle Earth pathogens. An alien microorganism might use different amino acids, different genetic encoding, different metabolic pathways. It could be harmless, or it could be deadly in ways we can't predict. The spacecraft would need quarantine protocols, containment systems, and the ability to study and respond to completely novel biological threats. Let's examine the political and social challenges of mounting an interstellar mission. No single nation could afford it. We're talking about costs in the tens of trillions of dollars sustained over decades just for development, then centuries for the mission itself. It would require unprecedented international cooperation, stable funding across multiple generations of politicians, and public support for a project with no immediate benefits. The International Space Station, costing about $150 billion and requiring cooperation between just a handful of nations, nearly failed multiple times due to political disagreements and budget constraints. Who decides who goes? If it's a generation ship, you're selecting the ancestors of everyone who will ever live on that ship. The genetic, psychological, and cultural implications are staggering. Do you select for genetic diversity, intelligence, physical health, psychological stability? Who makes these decisions? The selection process itself could take decades and spark intense ethical debates about eugenics, human rights, and the future of humanity. The legal framework for interstellar travel doesn't exist. Who owns Proxima b if we get there? Can a ship declare independence from Earth during the journey? What laws apply to children born in interstellar space? How do you enforce Earth's authority over a vessel that's light years away, with years of communication delay? The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but it was written when the Moon was our only conceivable destination. Interstellar travel would require entirely new international agreements that somehow remain binding for centuries. Cultural continuity presents unique challenges. Over a 200-year journey, the crew would develop their own culture, potentially diverging radically from Earth norms. Language evolves. English from 200 years ago is notably different from today's. Slang, idioms, and even grammar could shift. By arrival, the colonists might be culturally alien to Earth, unable to relate to the society that sent them. They might reject their mission, deciding they prefer life on the ship to colonizing an unknown world. Education on a generation ship would be unlike anything on Earth. Children would learn about oceans they've never seen, weather they've never experienced, animals that exist only in videos. How do you teach biology without ecosystems, geology without rocks, meteorology without weather? The knowledge base would gradually shift from experiential to purely theoretical. After several generations, Earth might become mythology, a paradise lost that some crew members might not even believe existed. The reproductive challenges of space travel are largely unknown. We don't know if humans can conceive in microgravity or if embryos can develop normally. The few studies on animal reproduction in space show serious problems: decreased fertility, abnormal development, higher miscarriage rates. Radiation exposure could damage DNA in eggs and sperm, causing birth defects that accumulate over generations. A generation ship would need artificial gravity, but rotating habitats bring their own engineering challenges and Coriolis effects that cause nausea and disorientation. Population control would be mandatory. The ship has finite resources, finite space. You can't allow unrestricted reproduction, but enforcing limits raises ethical nightmares. Who decides who can have children? What happens if someone has an unauthorized pregnancy? These decisions would need to be made by the ship's government, whatever form that takes, potentially creating a totalitarian system where reproductive rights are sacrificed for survival. Mental health services would be critical but challenging. The ship would need trained psychologists and psychiatrists, but also the ability to train new ones as the old ones age and die. Psychiatric medications would need to be manufactured on board. You can't pack centuries' worth of antidepressants. Some conditions might be untreatable. What do you do with someone who develops schizophrenia or violent psychosis? On Earth, we have institutions, treatments, and space to separate dangerous individuals from society. On a generation ship, every person is precious for genetic diversity, but one unstable individual could endanger everyone. The accumulated knowledge problem is real. The crew would need to maintain expertise in thousands of fields: medicine, engineering, agriculture, manufacturing, and more. But with a limited population, you can't have specialists in everything. Everyone would need to be a generalist, but complex problems often require deep expertise. The ship would need comprehensive databases and training programs, but even then, crucial knowledge could be lost if key individuals die unexpectedly. Consider cosmic rays again, but from a different angle. As particles approach the speed of light, their interaction with cosmic rays becomes more violent. At 90% of light speed, the cosmic ray flux increases dramatically from the crew's perspective. Hydrogen atoms become deadly radiation. The ship would be flying through a lethal hailstorm of particles, each impact generating secondary radiation that cascades through the ship. The shielding requirements become impossible. You'd need meters of dense material surrounding the entire vessel. Time dilation, which seems like it might help by shortening the journey from the crew's perspective, creates its own problems. At 90% light speed, the crew experiences about half the time that passes on Earth. But this means technologies and solutions developed on Earth after launch can't help them. By the time they arrive at Proxima B, Earth might have developed far superior technology, making their entire mission obsolete. They'd be technological orphans, cut off from humanity's advancing knowledge. The navigation precision required for interstellar travel exceeds anything we've achieved. An error of just 1 milliarc second in your initial trajectory, about the width of a human hair seen from 3 kilometers away, would cause you to miss Proxima b by millions of kilometers. The spacecraft would need to make continuous micro-adjustments, but every adjustment requires fuel. The navigation system would need to function perfectly for centuries, despite component degradation, cosmic ray damage, and the gradual drift of mechanical systems. Interstellar dust isn't empty space, it's filled with hydrogen atoms, dust grains, and larger particles. At high velocities, these become significant obstacles. A dust grain 1 millimeter across, hitting at 10% light speed, releases energy equivalent to tons of TNT. The ship would need some kind of shield or deflection system, but we have no technology capable of detecting and deflecting particles at these velocities. Even magnetic shields for charged particles would require enormous amounts of power and wouldn't stop neutral atoms or dust grains. The communication infrastructure needed to support an interstellar mission would be unprecedented. You'd need transmitters powerful enough to send signals across light years, receivers sensitive enough to detect faint replies, and the patience to wait years for responses. The Deep Space Network, our current best system, struggles to communicate with Voyager at just 22 billion kilometers. Proxima b is 2,000 times farther. The power requirements scale with the square of distance. We'd need transmitters millions of times more powerful, or receivers millions of times more sensitive. Data storage over centuries presents unique challenges. Modern storage media have limited lifespans. Hard drives fail after decades. Solid-state drives lose data without power. Optical media degrades. The ship would need multiple redundant storage systems, constant data verification and copying, and the ability to manufacture new storage devices. Critical information, like how to operate life support or navigate, would need even more redundancy. A single cosmic ray could corrupt vital data, so error correction and backup systems would be essential. Let's consider what we might find at Proxima b that could make the entire journey pointless. The planet might be in a runaway greenhouse state like Venus, with surface temperatures hot enough to melt lead. Or it might be in a permanent snowball state, frozen solid, with no hope of terraforming. The atmosphere might be toxic, full of methane, ammonia, or other compounds lethal to human life. The surface might be bombarded with radiation levels that make long-term habitation impossible, even with protective gear. Even if Proxima b is habitable, it would be alien in ways that could make colonization extremely difficult. The gravity would be different, affecting everything from how we walk to how our hearts pump blood. The day-night cycle, if it exists at all on a tidally locked world, would be nothing like Earth's. Seasonal patterns, if any, would be completely foreign. Our circadian rhythms, evolved over millions of years on Earth, would be constantly disrupted. Depression, insomnia, and other disorders could plague colonists permanently. The ethical implications of interstellar colonization are profound. If Proxima b has life, even microbial life, do we have the right to colonize it? Our arrival would inevitably contaminate the planet with Earth organisms, potentially driving native life to extinction. We could be committing xenocide, the elimination of an entire alien biosphere, for our own survival. The scientific loss would be incalculable. That alien life might hold keys to understanding the origin of life itself, or represent a completely different solution to the chemistry of living systems. Resource extraction on Proxima b would be starting from zero. On Earth, we have billions of years of geological processes that concentrated ores, created fossil fuels, and formed useful mineral deposits. Proxima b would have its own geology, but finding and extracting resources would require extensive exploration, mining equipment, and processing facilities, all of which would need to be either transported from Earth or built from scratch. The industrial base needed to sustain a technological civilization would take generations to establish. The colony would face a genetic bottleneck that could doom it to eventual extinction. Even with 10,000 initial colonists, far more than any proposed mission, genetic diversity would be limited. Harmful, recessive genes would become more common over generations. The colony might survive the journey only to slowly decline from accumulating genetic defects. Genetic engineering might help, but that raises ethical questions about human modification and requires technology that might not survive the journey intact. The terraforming challenge, if we even attempted it, would be humanity's greatest undertaking. Proxima b might require massive atmospheric modification, adding oxygen if there's none, removing toxic gases, adjusting pressure and temperature. On Mars, which is practically next door, we estimate terraforming would take tens of thousands of years with technology we don't possess. Proxima b, alien and unknown, could take even longer. The colonists would live in enclosed habitats for millennia, slowly working to transform a hostile world while hoping their descendants might one day walk under open skies. Consider the manufacturing chain required for even basic technology. To make a simple computer chip on Earth requires thousands of specialized components, rare earth elements, ultra-pure materials, and incredibly precise manufacturing equipment. The colony would need to recreate entire industries from scratch, mining equipment to extract raw materials, refineries to process ores, chemical plants to create pure elements, fabrication facilities to build components. Without any of these, the colony would quickly regress to pre-industrial technology as their Earth-built equipment inevitably failed. The spare parts problem alone could end the mission. Every machine has a lifespan. Every component will eventually fail. The colony would need to either bring replacements for everything, impossible given mass constraints, or develop the capability to manufacture anything from basic materials. A single critical component that can't be replaced or manufactured could cascade into mission failure. Imagine losing the ability to produce insulin for diabetics, or antibiotics for infections, or replacement parts for the air recycling system. Water on Proxima b is a complete unknown. Even if it exists, it might be locked in ice at the poles, contaminated with toxic minerals, or chemically bound in ways that make extraction difficult. The colony would need water for drinking, agriculture, manufacturing, and potentially fuel production. Without abundant, accessible water, the colony is doomed. Recycling helps but isn't perfect. Every loss would be irreplaceable. The psychological impact of water scarcity, even if merely perceived, could trigger conflict and hoarding behaviors that tear the colony apart. Agriculture in alien soil presents unknowns we can barely imagine. Earth plants evolved with specific soil bacteria, fungi, and nutrients. Proxima b's soil, if it exists, would have completely different chemistry. It might lack essential nutrients or contain toxic elements. The colonists would need to either transform alien soil with Earth bacteria, potentially destroying any native ecosystem, or grow everything hydroponically, requiring extensive infrastructure and resources. Crop failures wouldn't just mean hunger, they'd mean extinction. The medical challenges of an alien world multiply exponentially. Different gravity affects bone density, muscle mass, and cardiovascular health in ways we don't fully understand. Alien pathogens, if they exist, would be completely novel to our immune systems. Even non-biological threats like alien allergens or toxic compounds in the air or soil could cause health crises. The colony would need a fully equipped hospital, pharmaceutical manufacturing, and the ability to research and respond to completely unprecedented medical challenges. Children born on Proxima b would be aliens in a biological sense. Growing up in different gravity, they'd develop different bone structure, muscle distribution, possibly even organ placement. Their immune systems would adapt to Proxima b's environment. Within a few generations, they might be so physiologically different from Earth humans that returning to Earth would be impossible. They'd be crushed by Earth's gravity, poisoned by Earth's atmosphere, or vulnerable to Earth diseases. humanity would have irreversibly branched into separate species. The knowledge preservation challenge extends beyond just storing information. Context and understanding matter. Imagine trying to maintain knowledge of Earth's ecosystems when no living person has seen a forest, ocean, or mountain. Abstract knowledge without experiential understanding becomes meaningless over generations. The colonists might have encyclopedias describing Earth, but could they truly understand what they've never experienced? Would they even care about preserving Earth knowledge when their daily survival depends on understanding Proxima b? Cultural artifacts would be limited to what can be digitized. No original paintings, sculptures, or physical books could make the journey. The mass constraints forbid it. Music, literature, and film would exist only as files, vulnerable to corruption or loss. The colony's culture would inevitably diverge from Earth's, creating their own art based on their unique experiences. Within centuries, they might view Earth culture as foreign and irrelevant, a curiosity from ancestors they never knew. The philosophical implications run deep. If the colony succeeds, are they still human, still part of Earth's civilization? Or are they something new, Proximans perhaps, with their own destiny separate from Earth? Would Earth have any moral authority over them? Could we even understand each other after centuries of divergent evolution and culture? The successful colonization of Proxima b might not extend humanity's reach, but fragment it into isolated pockets that gradually become alien to each other. Let's examine the latest observations from our most powerful telescopes. The James Webb Space Telescope has revolutionized exoplanet science, but Proxima b remains frustratingly elusive. Its proximity to Proxima Centauri makes direct observation extremely difficult, like trying to see a firefly next to a searchlight. We've learned more about planets hundreds of light years away than about our nearest neighbor. This ignorance means any mission to Proxima b would be launching into the unknown, risking everything on a world we barely understand. The recent discovery of Proxima c, a possible super-Earth, orbiting farther from Proxima Centauri, complicates our understanding of the system. Multiple planets mean complex gravitational interactions that could affect Proxima b's orbit over time. The system might be unstable over geological timescales, or there might be additional planets we haven't detected yet. Imagine arriving after centuries of travel to find Proxima b's orbit has shifted, making it uninhabitable, or discovering massive planets whose gravity makes navigation treacherous. Solar flares from Proxima Centauri pose an existential threat we're only beginning to understand. Red dwarf stars like Proxima Centauri are notorious for violent outbursts. In 2019, Proxima Centauri released a flare so powerful it briefly made the star 7,000 times brighter in ultraviolet light. Such flares could strip away atmosphere, sterilize the surface, and destroy any technology not hardened against extreme radiation. The colony would need to predict, prepare for, and survive these stellar tantrums indefinitely. The tidal locking problem creates a world unlike anything in our solar system. One side of Proxima b likely faces its star permanently, creating a day side with scorching temperatures and a night side frozen in eternal darkness. The only potentially habitable region would be the twilight zone, a narrow band where day meets night. But this region would experience constant fierce winds as hot air from the day side meets cold air from the night side. The colony would exist in permanent hurricane conditions, making surface operations extremely challenging. Even if Proxima b has an atmosphere that moderates these temperature extremes, it would create its own challenges. The atmosphere would need to be thick enough to transfer heat, but not so thick that it creates a runaway greenhouse effect. It would need the right composition to be breathable, or at least convertible to breathable air. The magnetic field question is crucial. Without one, solar wind from Proxima Centauri would gradually strip away any atmosphere, as happened to Mars. We have no idea if Proxima b has a magnetic field, and no way to generate one artificially if it doesn't. The mission architecture problem has no good solutions. Do you send robots first to prepare the way? That adds decades or centuries to an already impossibly long timeline, and the robots would need to function autonomously for all that time. Do you send humans in hibernation? We have no technology for long-term suspended animation, and the biological challenges of centuries-long hibernation might be insurmountable. Do you send a generation ship? The psychological and sociological challenges could doom the mission before it arrives. Consider the staging problem. You can't launch an interstellar mission from Earth's surface. The rocket equation makes that impossible. You'd need to construct the spacecraft in orbit or at a Lagrange point. But building something so massive in space would require hundreds or thousands of launches, orbital construction facilities we don't have, and assembly techniques we haven't developed. The International Space Station, tiny by comparison, took over a decade to construct with the combined resources of multiple nations. The testing problem is unsolvable. On Earth, we test everything extensively before committing to a mission. Aircraft undergo thousands of hours of testing. Spacecraft complete multiple ground tests and usually unmanned flights before carrying crew. But you can't test a centuries-long interstellar journey. You can't verify that your closed-loop life support will work for 200 years. You can't confirm that your spacecraft structure will survive decades of cosmic radiation. The first interstellar mission would be the test, with billions of lives and trillions of dollars at stake. The trajectory optimization problem becomes nightmarish over interstellar distances. You need to account for the gravitational influence of not just the Sun and Proxima Centauri, but also potentially Jupiter, Saturn, and other massive bodies. Over centuries, small gravitational perturbations accumulate into major course deviations. The spacecraft would need to predict and compensate for gravitational influences while having limited fuel for corrections. One miscalculation early in the journey could mean missing the target system entirely, with no way to recover. The propellant storage problem over centuries presents challenges we've never faced. Chemical propellants degrade over time, solid fuels crack and become unstable, liquid fuels develop impurities, and cryogenic fuels like liquid hydrogen slowly boil off despite the best insulation. Nuclear fuels remain stable longer, but require heavy shielding that adds mass. Antimatter, if we could produce and store it, would need magnetic containment systems that couldn't fail for even a microsecond over centuries. A single containment failure would vaporize the entire spacecraft in an instant. Let's talk about something nobody wants to discuss: mission failure scenarios. What happens when things go catastrophically wrong a light year from Earth? An epidemic that kills most of the crew? A reactor meltdown that contaminates the ship? A navigation failure that sends you into deep space with no way to correct course? On Earth missions, we have abort procedures, rescue possibilities, mission control support. On an interstellar mission, you're absolutely alone. Every failure scenario needs to be survivable with only onboard resources, or the mission ends in death and darkness. The recycling efficiency problem compounds over time. No recycling system is 100% efficient. The ISS water recovery system, one of our best, still loses about 7%. Over 200 years, those losses accumulate catastrophically. Starting with 10,000 tons of water and losing just 1% per year, you'd have only 1,350 tons left after 2 centuries. But it's worse. Recycling equipment degrades, efficiency drops over time, and spare parts run out. The colony might survive the journey only to slowly die of thirst, as their recycling systems fail. Consider the debris field problem around Proxima Centauri. Every star system has its own collection of asteroids, comets, and dust. We know almost nothing about what surrounds Proxima b. There could be dense asteroid belts, active comets, or debris from planetary formation. The spacecraft would be entering this unknown environment at enormous velocity with no way to scout ahead. One collision with an unseen asteroid would end the mission instantly. The colony ship would need detection and deflection systems for objects we can't even confirm exist. The personality selection paradox is unsolvable. You want psychologically stable individuals for the mission, but psychological stability on Earth doesn't predict behavior in unprecedented situations. The most stable person might crack under the pressure of permanent exile from Earth. Someone with mild anxiety on Earth might thrive when given the purpose and structure of an interstellar mission. Psychological testing can't predict how someone will handle watching Earth disappear forever, living their entire life in an enclosed space, or knowing their children will never see a blue sky. Genetic screening creates ethical nightmares. Do you exclude people with genetic predispositions to cancer, heart disease, or mental illness? That might seem logical until you realize you're practicing eugenics. Many of humanity's greatest contributors had genetic conditions that would disqualify them from an interstellar mission. Stephen Hawking had ALS. Einstein might have had autism. Would we exclude them? The genetic diversity needed for a viable colony might require including people with health conditions, but providing medical care for genetic conditions over centuries adds complexity and resource demands. The education infrastructure would need to be self-perpetuating. Teachers would need to train their replacements before they die. Knowledge would need to be preserved across generations without degradation. But education isn't just information transfer. It requires practical experience. How do you train doctors without a variety of patients? Engineers without diverse problems to solve? Scientists without new phenomena to study? The colony's knowledge base would inevitably narrow to only what's immediately useful for survival, losing the breadth that enables innovation. Language drift over centuries would create communication problems with Earth. Languages evolve constantly. New words emerge, meanings shift, grammar changes. The English of Chaucer's time is barely comprehensible to modern speakers. After 200 years in isolation, the colony's language would diverge significantly from Earth languages. Technical manuals from Earth might become unreadable. Communication with Earth would require translation. The colony might need to maintain classical Earth languages artificially, like we preserve Latin, just to access historical knowledge. The moral injury of the mission would affect everyone differently. Knowing you've condemned your children to live and die in a metal tube, never experiencing Earth, would weigh on parents. Children might resent their parents for choosing this life for them. The middle generations, who neither chose the mission nor will see its completion, might feel their lives are meaningless, just biological bridges between departure and arrival. This existential despair could manifest as depression, nihilism, or destructive behavior that threatens the mission. Resource conflicts would be inevitable. Even with careful planning, some resources would run low. Who decides who gets scarce medications? How much water goes to agriculture versus human consumption? If life support can only sustain 9,000 people, but there are 10,000 aboard, who dies? These decisions would require governance structures that balance survival with human rights, efficiency with compassion. But history shows that resource scarcity often leads to authoritarianism, violence, and the breakdown of social order. The technological regression risk is real. Complex technology requires complex supply chains. If the colony can't manufacture microchips, they can't replace computers. Without computers, they lose automation, navigation, and data storage. They might maintain mechanical and simple electrical systems longer, but eventually they'd face a choice: spend enormous resources trying to maintain Earth technology, or accept regression to a simpler technological level that they can sustain with local resources. Mental health treatment over generations would face unique challenges. Therapy techniques developed on Earth might not work in the colony's environment. Medications would need to be manufactured from raw materials, requiring a complete pharmaceutical industry. New mental health conditions might emerge from the unique stresses of interstellar travel. The colony would need to develop its own psychiatric practices, possibly discovering that Earth's diagnostic categories don't apply to their reality. The criminal justice problem has no easy answers. On Earth, we can imprison dangerous individuals, sometimes for life. On a colony ship, every person is precious for genetic diversity and labor. You can't afford to lock someone up for decades, but you also can't allow violent criminals to roam free. Execution wastes genetic resources. Exile is impossible. The colony would need to develop rehabilitation techniques that actually work, or find ways to manage dangerous individuals without traditional incarceration. Cultural traditions would either fossilize or evolve beyond recognition. Religious practices developed on Earth might lose meaning in space. What does Easter mean when there are no seasons? How do you face Mecca when you're light years from Earth? New religions might emerge based on the colony's experiences. Earth religions might be preserved as historical curiosities or abandoned as irrelevant to the colony's reality. This cultural evolution could create generational conflicts as older colonists try to preserve Earth traditions while younger ones develop their own. The immunity degradation problem would worsen over generations. In Earth's biosphere, our immune systems constantly encounter mild challenges that keep them trained. In the sterile environment of a spacecraft, immune systems would weaken from lack of stimulation. The colony might need to deliberately maintain controlled populations of harmless bacteria just to keep immune systems functional. But determining which organisms are truly harmless over centuries would be gambling with the colony's survival. Archaeological evidence suggests every human society develops art, music, and storytelling. But the colony's art would be alien to Earth's sensibilities. Music might evolve based on the ship's ambient sounds, ventilation systems, engines, recycling equipment. Visual art would be constrained by available materials and spaces. Stories would center on the journey, the ship, the mission. Within generations, Earth's artistic traditions might seem as foreign as ancient cave paintings do to us. The navigation beacon problem is rarely discussed. Over centuries, the spacecraft's position uncertainty grows. You need fixed reference points for navigation, but stars have proper motion. They move relative to each other. Pulsars, our best cosmic lighthouses, have timing variations. The spacecraft would need to constantly recalibrate its position using multiple references, accounting for relativistic effects, and correcting for accumulated errors. One significant navigation error could mean arriving at empty space where Proxima B should be. Sleep deprivation would be chronic. The ship's environment would never be perfectly quiet. Pumps, fans, and life support systems create constant noise. Light pollution from essential systems would disrupt circadian rhythms. The lack of natural day-night cycles would require artificial substitutes that never quite feel right. Poor sleep degrades decision-making, emotional regulation, and physical health. Over generations, chronic sleep deprivation could reduce the colony's cognitive capabilities, making complex problem-solving increasingly difficult. The pregnancy and childbirth challenges in space remain largely unknown. We assume artificial gravity would help, but how much is needed? What about the radiation exposure during critical fetal development periods? The colony would need complete obstetric and neonatal facilities, including the ability to handle premature births, birth defects, and pregnancy complications. Every lost pregnancy wouldn't just be a personal tragedy, but a blow to the colony's genetic future. The colony ship would face an insidious problem we rarely consider: metal fatigue from vibration. Every pump, every fan, every rotating component creates vibrations that propagate through the ship's structure. Over decades, these micro-vibrations cause stress fractures in metal components. On Earth, we inspect and replace fatigued parts regularly. The Golden Gate Bridge has had its cables inspected and repaired continuously since 1937. But a colony ship can't stop for maintenance. Critical structural failures could cascade through the vessel, potentially causing explosive decompression that kills everyone in seconds. Consider the data degradation nightmare. Digital storage isn't permanent. Bit rot is real. Cosmic rays flip bits, magnetic fields weaken, electrical components degrade. The colony would need to constantly copy and verify petabytes of crucial data, medical databases, technical manuals, cultural archives, navigation software. But each copy introduces potential errors. After centuries, would their medical database still be accurate? Would critical engineering specifications have accumulated fatal errors? They'd need multiple redundant storage systems and constant data verification, consuming enormous computational resources. The colony's children would face developmental challenges we can't predict. Human development evolved in Earth's environment, specific gravity, magnetic fields, light spectra, and atmospheric pressure. Children developing in artificial gravity might have different neural pathways, altered depth perception, or modified motor skills. Their brains might wire differently in response to the ship's environment. These changes could accumulate over generations, creating humans increasingly adapted to spacecraft life, but potentially unable to function on a planetary surface. Food variety would collapse to whatever can be grown efficiently in artificial conditions. No seasons means no seasonal foods. No wild animals means no hunting or fishing. No diverse ecosystems means no foraging. The colony would likely subsist on a handful of crops optimized for nutrition and growth speed: algae, potatoes, soybeans. Psychological studies show that food monotony leads to decreased appetite, depression, and social tension. Imagine eating essentially the same meals for your entire life, knowing your children and grandchildren will too. The mineral deficiency problem could doom the colony slowly. Earth's soil contains trace elements accumulated over billions of years: selenium, iodine, zinc, copper. These micronutrients are essential for human health in tiny quantities. The colony's closed-loop agriculture would need to carefully manage every element. But losses are inevitable: atoms bound in indigestible compounds, trace amounts in waste that can't be recovered. Over time, deficiencies would accumulate. The colonists might survive the journey only to develop scurvy, goiter, or other deficiency diseases on arrival. Mechanical skills would atrophy over generations. The first generation would include trained engineers and technicians, but their children would learn from manuals and simulations, hands-on experience with diverse systems. By the third or fourth generation, practical knowledge would be largely theoretical. When critical systems fail, would anyone remember how to actually turn a wrench, solder a connection, or diagnose a mechanical problem? The colony might have all the knowledge needed for repairs, but lack the practical skills to implement them. The spare parts inventory would be a logistical nightmare. You need parts for everything: pumps, valves, circuits, seals. But you can't predict what will fail when. Stock too many of one component, and you've wasted precious mass. Too few, and a single failure dooms the mission. Parts would need to be generic and adaptable, standardized components that could be modified for multiple uses. But this limits efficiency and increases complexity. The colony would need massive 3D printing capabilities, raw materials, and the knowledge to fabricate anything from scratch. Corrosion would be a constant enemy. Oxygen and water, essential for life, are also incredibly corrosive. Metal pipes carrying water develop rust, weakening over time. Electrical connections oxidize, increasing resistance and generating heat. Even stainless steel corrodes eventually under the right conditions. The colony would need continuous inspection and replacement programs, but in a closed system, where do replacement materials come from? You'd need to recycle corroded components, purify the metals, and remanufacture parts, an energy-intensive process that might not be sustainable. The power grid would be impossibly complex and fragile. Every system needs electricity, life support, computers, lighting, food production. The grid would need multiple redundancies, but each backup system adds complexity and potential failure points. A cascading power failure could kill everyone in minutes. The colony would need engineers capable of managing electrical loads, predicting failures, and rerouting power instantly. But after generations, would anyone truly understand the entire system? Or would they just follow procedures written by long-dead ancestors? Social stratification would emerge inevitably. Even starting with an egalitarian society, differences in skills, personalities, and circumstances would create hierarchies. Children of engineers might receive better technical education. Families controlling critical resources might accumulate power. Over generations, rigid class systems could develop. History shows that isolated communities often develop strict social hierarchies. The colony might arrive at Proxima b not as unified explorers, but as a stratified society with built-in conflicts. The justice system would need to handle crimes that don't exist on Earth. Sabotaging life support isn't just murder, it's potential genocide. Hoarding resources threatens everyone's survival. Having unauthorized children affects generations of genetic planning. The colony would need laws and punishments for crimes we can't imagine, developed and enforced by people who've never experienced Earth's legal traditions. Justice might become harsh by necessity. The margin for error is too small for lengthy legal proceedings or rehabilitation attempts that might fail. Memory degradation of Earth would be profound. The first generation would have vivid memories of blue skies, forests, and oceans. Their children would know Earth only through stories and videos. By the third generation, Earth would be mythology, a perfect paradise lost that might not seem real. This disconnection could lead to two dangerous extremes, either abandoning the mission as pointless or developing an unrealistic idealization of Earth that sets impossible expectations for Proxima b. The manufacturing chain would be incredibly fragile. Making a simple bolt requires metal extraction, refining, alloying, machining, and quality control. Each step requires specialized equipment that itself needs maintenance and replacement. If any link in this chain breaks, if the metal refinery fails, if the machining tools wear out, if quality control systems degrade, the entire manufacturing capability collapses. The colony would need multiple parallel manufacturing chains, but this multiplies complexity and resource requirements. Hygiene standards would be difficult to maintain. Water is precious, so showers would be rare and brief. Laundry would be minimized to save water and energy. Personal space would be cramped, making privacy for basic hygiene challenging. Studies of historical long voyages show that hygiene degradation leads to disease, social conflict, and psychological distress. The colony would need to balance resource conservation with maintaining sufficient cleanliness for health and social cohesion. The genetic counseling burden would be enormous. Every pregnancy would need genetic screening to avoid accumulating harmful mutations. Couples might be told they can't have children together due to genetic incompatibility. Some individuals might be strongly encouraged to reproduce despite personal preferences, while others might be discouraged or prevented. This level of reproductive control, while necessary for genetic diversity, would create profound ethical dilemmas and personal traumas. Equipment standardization versus specialization would be an impossible balance. Standardized equipment is easier to maintain and replace but less efficient for specific tasks. Specialized equipment works better but requires unique parts and expertise. The colony would need to somehow maintain both. standardized systems for critical functions and specialized equipment for essential tasks. This dual approach multiplies complexity, training requirements, and resource needs. The knowledge preservation system would need unprecedented sophistication. It's not enough to store information. It needs to be accessible, understandable, and relevant across generations. Technical manuals would need constant updating as equipment is modified or replaced. Languages would need to be preserved even as they evolve. Cultural knowledge would need context that might be lost over time. The system would need to be self-maintaining, self-correcting, and adaptable to changes we can't predict. Radiation exposure would accumulate differently for each person. Those who perform exterior repairs would receive higher doses. Pregnant women would need extra shielding. Children would be more vulnerable to radiation damage. Over time, this would create a radiation caste system. Those who've received too much exposure relegated to interior tasks, while those with lower exposure perform critical exterior work. This could create resentment, health disparities, and social divisions that threaten mission cohesion. The entertainment problem might seem trivial but could prove critical. Humans need stimulation, variety, and fun, but entertainment options would be limited to what can be stored digitally or created on board. No sports requiring large spaces, no outdoor activities, no travel or exploration. The same movies, music, and games for generations. Boredom and monotony lead to depression, aggression, and antisocial behavior. The colony would need to constantly create new entertainment, but would their creative output be enough to satisfy human psychological needs? The microbial ecosystem management would be a delicate balance between life and death. The colony ship would need beneficial bacteria for digestion, waste processing, and food production. But microbes evolve rapidly. E. coli can go through 20,000 generations during the journey. Beneficial bacteria could mutate into pathogens. The colony would need microbiologists capable of monitoring and managing bacterial evolution. But how do you control organisms that reproduce every 20 minutes? One escaped pathogenic strain in a closed environment could kill everyone before countermeasures are developed. Let's examine the tool degradation crisis. Every tool wears out, drill bits dull, wrenches round off, measuring instruments lose calibration. On Earth, we replace worn tools without thinking. The colony would need to manufacture every replacement tool from raw materials, but making tools requires tools. If the tool-making tools wear out, the colony faces a cascade of technological regression. They'd need multiple tool-making workshops with different technologies, mechanical, electrical, chemical, to ensure at least one remains functional. The ethical burden on medical professionals would be crushing. With limited resources, doctors would face impossible choices: use the last antibiotics on an elderly engineer or save them for potential childhood infections. Attempt a risky surgery with improvised equipment or let the patient die. Euthanasia might become necessary for terminal patients consuming resources others need. Medical professionals would carry the psychological weight of these decisions for life, potentially leading to burnout, substance abuse, or suicide among the very people the colony needs most. Water ice on Proxima B, if it exists, might be locked in forms we can't use. It could be mixed with perchlorates like on Mars, making it toxic. It might be buried under kilometers of rock or frozen CO2. The chemical composition could be different from Earth ice, heavy water or ice with dissolved minerals that make extraction energy intensive. The colony might arrive to find water everywhere, but none of it usable without massive infrastructure they can't build. The waste heat problem in space is counterintuitive but critical. Every joule of energy used on the ship eventually becomes heat, from computers, lights, human bodies, industrial processes. In space's vacuum, the only way to lose heat is radiation, which is slow. Too much activity and the ship overheats, too little and it freezes. The colony would need massive radiators that are vulnerable to micrometeorite damage. As equipment degrades and becomes less efficient, waste heat increases. The ship might slowly cook itself to death as systems become less efficient over time. Consider the cascade failure scenario. One system fails, increasing load on backups. Backups wear out faster under increased load. Their failure cascades to other systems. Life support fails, forcing emergency measures. Emergency systems consume more power, stressing the electrical grid. The grid fails, knocking out computers. Without computers, navigation fails. Each failure multiplies into others. The colony would need to prevent not just individual failures, but cascading chains that could destroy everything in hours. The pharmaceutical manufacturing challenge would be staggering. Modern drugs require precise chemical synthesis, ultra-pure reagents, and exact conditions. The colony would need to produce hundreds of different medications, antibiotics, antivirals, anesthetics, hormones, psychiatric drugs. Each requires different equipment, raw materials, and expertise. Insulin for diabetics, epinephrine for allergic reactions, chemotherapy for cancers. Without Earth's vast pharmaceutical infrastructure, the colony would watch people die from treatable conditions. Time perception would warp over generations. The first generation would measure time by Earth years, maintaining calendars and holidays from home. But what meaning does winter have for children who've never experienced seasons? Why celebrate the new year when every day is identical? The colony might develop their own time measurements based on ship rotations or life support cycles. This temporal disconnect from Earth would deepen their psychological isolation and cultural divergence. The apprenticeship system would be critical but fragile. Essential skills would need to be passed from master to student across generations. But what if the master dies before training is complete? Written manuals can't capture the subtle intuitions developed through years of practice. The colony would need multiple people trained in every critical skill, but with limited population, this might be impossible. Crucial knowledge could be lost in a single accident or illness. Material fatigue would affect everything simultaneously. It's not just one component failing, it's everything degrading together. Seals throughout the ship would become brittle. Metal structures would develop stress fractures, plastics would become fragile, electronic components would drift from specifications. The colony would face not isolated failures, but a general degradation of everything, requiring more maintenance than they could possibly perform. The colony's government would face challenges no Earth authority has encountered. They'd need to balance individual freedom with collective survival, democracy with the need for quick decisions, tradition with adaptation. Should Earth laws apply light years away? Can the colony declare independence? Who decides if the mission should be abandoned? Government structures that work on Earth might fail catastrophically in the colony's unique environment. Pregnancy complications would be deadlier than on Earth. No option to fly in specialists, no advanced NICU for premature babies, limited blood for transfusions. The colony would need obstetricians, but also the equipment and expertise for emergency C-sections, treatment of eclampsia, management of gestational diabetes. Every pregnancy would carry significant risk. The psychological toll on women, knowing that pregnancy might kill them and help is impossible, would be immense. The navigation computer problem extends beyond just hardware. Software accumulates errors over time, memory leaks, corrupted databases, obsolete code that no one understands. The colony would need programmers capable of maintaining and updating navigation software written in languages decades or centuries old, but programming skills atrophy without diverse challenges. After generations of maintenance programming, would anyone be capable of fundamental rewrites when necessary? Social media and communication within the ship would evolve strangely. Everyone would know everyone, no strangers, no privacy, no escape from social dynamics. Rumors would spread instantly through the confined population. Social conflicts couldn't be avoided by unfriending or blocking. You'd still see your enemies daily. The colony would need to develop new social norms for managing conflict in inescapable proximity. The child development environment would be unprecedented in human history. No running in open fields, no climbing trees, no swimming in lakes, no pets beyond what's essential for the ecosystem. Children's games would adapt to confined spaces and artificial gravity. Their psychological development would be shaped by an environment no human child has experienced. Would they still be psychologically human in ways we recognize? Dust accumulation might seem minor but could prove deadly. Human skin cells, fabric fibers, and other particles constantly fill the air. In gravity, dust settles and can be cleaned. In microgravity sections, it floats, clogging filters, coating electronics and entering lungs. The ISS spends significant time cleaning to prevent dust accumulation. Over centuries, dust could degrade equipment, cause respiratory problems, and create fire hazards. Yet cleaning consumes water and energy the colony can't spare. The replacement parts paradox would worsen over time. As the ship ages, parts fail more frequently. But manufacturing replacements requires equipment that's also aging. Eventually, they'd need replacement parts to make replacement parts. The colony might face choosing which systems to maintain and which to abandon. Life support obviously takes priority, but what about entertainment systems that maintain morale? Scientific equipment for studying Proxima b, the communication system for contacting Earth? Muscle memory would be lost across generations. The first generation would remember how to swim, ride bicycles, climb stairs. Their children would learn these movements only in theory or limited simulation. By arrival at Proxima b, colonists might need to relearn basic planetary movements, walking on uneven ground, judging distances without corridor walls, navigating without ceiling references. The adjustment period could be dangerous, with falls and accidents common. The archive integrity problem would compound over time. Digital archives would need constant verification against corruption. Physical samples, seeds, genetic material, cultural artifacts would degrade despite preservation efforts. The colony might arrive at Proxima b with corrupted databases, non-viable seeds, and degraded genetic samples. Their carefully preserved Earth heritage could be lost to entropy, leaving them with fragments and corrupted files. Power storage systems would degrade unpredictably. Batteries lose capacity over time, even when not used. Nuclear fuel decays on its own schedule. Solar panels, if used, would degrade from radiation exposure. Fuel cells would lose efficiency. The colony would need multiple power storage technologies, but each adds complexity and failure points. A power storage crisis could force impossible choices: shut down science labs to maintain life support, or reduce lighting to preserve food production. The colony ship would become humanity's most ambitious tomb if we're honest about the probabilities. Every analysis, every simulation, every honest assessment points to the same conclusion. The technical, biological, psychological, and logistical challenges compound into impossibility. We're not talking about solving one or two major problems. We're talking about solving thousands of interconnected challenges, any one of which could doom the mission. The margin for error is zero, the backup options non-existent, and the consequences of failure absolute. But here's what makes us human. We dream anyway. Despite knowing the crushing realities, the insurmountable obstacles, the near-certain failure, we still look up at Proxima Centauri and wonder, what if? This isn't foolishness. It's the same drive that led our ancestors to cross oceans on wooden boats, to strap themselves to rockets aimed at the moon, to split the atom and decode the genome. Every impossible thing remains impossible until suddenly one day it isn't. The detection of Proxima b changed everything and nothing simultaneously. Everything, because now we have a target. A real world that might harbor life, or at least the conditions for it. Nothing, because knowing it exists doesn't bring us any closer to reaching it. It's like a prisoner discovering there's a world outside their cell. The knowledge is both liberating and tormenting. We can study Proxima B's orbit, estimate its mass, speculate about its conditions, but we can't touch it, can't sample it, can't know its true nature. Future telescopes might reveal more about Proxima B. The proposed Habitable Worlds Observatory could potentially detect biosignatures, oxygen, methane, or other gases that might indicate life. Ground-based telescopes with 30-meter mirrors could resolve details we can only dream of today. We might discover that Proxima B has oceans, continents, or even city lights. Or we might find it's a barren rock, no more hospitable than our moon. Each discovery would be bittersweet, knowledge gained about a world we cannot reach. The philosophical implications of our isolation are staggering. If faster-than-light travel is truly impossible, if the distances between stars are truly insurmountable, then every inhabited world is fundamentally alone. The universe might teem with life, with civilizations, with wonders beyond imagination, but each would be forever isolated in their own stellar bubble. We might detect each other's radio signals, exchange messages across the void, but never meet, never touch, never share the same sunset. This cosmic loneliness might be why we don't see evidence of advanced civilizations, not because they don't exist, but because they've all reached the same conclusion we're reaching: the stars are forever out of reach. They might have turned inward, focusing on their own worlds, their own solar systems, accepting the boundaries nature has imposed. The great silence of the cosmos might not be emptiness, but resignation. Countless civilizations who've accepted what we're still struggling to acknowledge. Yet the human spirit rebels against limitations. We're already imagining solutions that seem like magic today. Breakthrough. Starshot pushes the boundaries of what's possible with light sails and lasers. Fusion rockets remain perpetually 20 years away, but inch closer to reality. Some physicists explore exotic concepts like Alcubierre drives and traversable wormholes, searching for loopholes in Einstein's cosmic speed limit. These might all fail, probably will fail, but the attempt itself has value. The search for solutions drives innovation that benefits us regardless. Developing closed-loop life support for interstellar travel improves sustainability on Earth. Studying radiation shielding for deep space helps cancer treatment. Advancing artificial intelligence for autonomous spacecraft decision-making revolutionizes technology at home. Even if we never reach Proxima B, the attempt to solve these problems pushes humanity forward. The journey becomes more important than the destination. Consider what we've learned just from trying. The Voyager missions, originally planned for 4 years, have operated for 46 and taught us about the interstellar medium. The ISS has shown us how humans adapt to space, revealing medical challenges we never anticipated. Every Mars rover, every asteroid mission, every space telescope adds pieces to the puzzle. We're slowly, methodically, learning what it takes to survive beyond Earth, even if that knowledge ultimately shows us our limits. The discovery of exoplanets has exploded our understanding of planetary systems. We've found hot Jupiters orbiting closer to their stars than Mercury, super-Earths with no solar system analogue, planets orbiting binary stars like science fiction's Tatooine, water worlds, lava worlds, diamond worlds. Each discovery shows us how unique and precious Earth is, how unlikely our exact conditions are to be replicated elsewhere. Proxima B might be Earth-sized and in the habitable zone, but that guarantees nothing about its actual habitability. Here's a humbling thought. We might be living in the brief window where we know other worlds exist, but can't reach them. For all of human history until 1995, we didn't know if planets existed beyond our solar system. In the cosmic future, if humanity survives, we might develop technologies that make interstellar travel routine. We're in the painful adolescence of our species, aware of the wider universe but not yet capable of exploring it. Future humans might look back at our era with sympathy, the way we look back at ancient astronomers who could see the planets but not understand what they were. The Proxima Centauri system might not even be the best target. TRAPPIST, 139 light-years away, has 7 terrestrial planets, several potentially habitable. But it's 10 times farther than Proxima b Ross, 128b, 11 light-years away, might be more Earth-like. Wolf, 1061c, 14 light-years distant, sits firmly in its star's habitable zone. We're surrounded by potentially habitable worlds, each impossibly distant, each tantalizing us with possibilities we can't explore. The red dwarf problem affects most nearby potentially habitable worlds. 3/4 of stars in our neighborhood are red dwarfs like Proxima Centauri, small, cool, and prone to flares. Their habitable zones are so close that planets are likely tidally locked. These stars were once thought ideal for life because they burn for trillions of years. Now we know their flare activity might sterilize any nearby planets. The worlds we can almost reach might be the least likely to harbor life. But let's dream for a moment. Imagine we solve every challenge. We build true fusion rockets or antimatter drives. We develop perfect closed-loop life support. We cure the biological effects of radiation and microgravity. We create artificial intelligence that can manage complex systems for centuries. We establish a colony on Proxima b. What then? That colony would face the same isolation from us that we face from Earth. Communication would take years, trade would be impossible. They'd be alone, developing their own culture, their own solutions, their own destiny. The successful colonization of Proxima b wouldn't unite humanity, it would divide it. Within generations, Proximans would be as foreign to Earth humans as we are to our distant ancestors. Their concerns wouldn't be our concerns, their culture wouldn't be our culture. They might even evolve differently, adapted to Proxima b's environment. We wouldn't have expanded humanity, we'd have created a new branch of it, forever separated by the void. This brings us back to Earth, to our pale blue dot, to the only world we know can support life. Every impossibility about reaching Proxima b reminds us how precious Earth is. We evolved here, adapted to this specific gravity, this atmospheric composition, this magnetic field, these seasons. Earth isn't just our home, it's part of us at a molecular level. Our DNA is shaped by Earth's radiation environment. Our circadian rhythms match Earth's rotation. Our bones are built for Earth's gravity. The dream of Proxima b, impossible as it may be, serves a purpose. It reminds us that worlds exist beyond our own. It drives us to develop new technologies. It forces us to confront our limitations and our potential. It makes us ask fundamental questions about our place in the universe and our responsibilities to future generations. Even if we never reach it, Proxima b has already changed us by existing, by being known, by being dreamed about. So where does this leave us? We will never reach Proxima b. Not with our current understanding of physics, not with any technology we can reasonably envision. The distances are too vast, the challenges too numerous, the human lifespan too short. But we'll keep trying, keep pushing boundaries, keep asking what if, because that's what humans do. We dream impossible dreams and occasionally, just occasionally, we make them possible. The real tragedy isn't that we can't reach Proxima b, it's that we might stop trying to understand it, stop pushing the boundaries of what's possible, stop dreaming of the stars. Every generation should push a little farther, understand a little more, dream a little bigger. Maybe we'll never walk on Proxima b, but perhaps we'll find something better. A deeper understanding of our universe, our limitations, and ourselves. I want to leave you with this thought. 4.2 light-years is an impossible distance for human travel. but it's nothing to light itself. Every second, photons that left Proxima b 4.2 years ago reach Earth, carrying information about that distant world. In a very real sense, Proxima b touches us constantly through these messengers of light. We may be separated by an unbridgeable gulf, but we're connected by the same physics, the same light, the same universe. Thank you for joining me on this journey through the harsh realities and persistent dreams of interstellar travel. If this exploration has made you think differently about our cosmic situation, please share your thoughts in the comments. Subscribe to continue exploring the universe's biggest questions and most humbling truths. Remember, we might be trapped in our solar system, but our minds can wander among the stars. The fact that we can know Proxima b exists, that we can study it from afar, that we can dream about it, that itself is a kind of miracle. We are stardust contemplating stars, a way for the universe to know itself. And even if we never reach Proxima b, the fact that we tried, that we dreamed, that we pushed against the impossible, that's what makes us human. Keep looking up, keep asking why, and never stop wondering about what lies beyond our reach. Because in the end, the greatest journeys aren't measured in light years traveled, but in understanding gained. Until next time, this is your reminder that we live in an age of cosmic discovery, where new worlds are found regularly, where the impossible becomes possible through human ingenuity, and where the greatest adventure, understanding our universe, has only just begun. The stars may be out of reach, but they're not beyond our comprehension. And in that knowledge, in that ceaseless curiosity, we find not limitation, but liberation. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And I am sure you will love this other video at the left side of the screen. This is why we will never reach Mars. In this video, discover the real science behind why Mars colonization is far more impossible than you've been told. See you there.